Now we begin to the third part of the particle kinematics, which is 1.3, plane curve motion. Plane curve motion. So that first we can discuss about the Cartesian decomposition. That if we suppose we have a small object sphere and we eject it at an angle like cross the x-axis, and if we ignore the air resistance, it will be a parabola, right? So if like we consider a satellite moving around the Earth in the eclipse, it's going around a circular orbit relative to the Sun. The Earth is going an elliptical orbit, which is the Sun is at a focus. And those are all plane curve motions. So if we have a rectangle coordinate O, X, Y, we have a particle point and its position can be represented by a vector r. And we can write down r equals x I roof plus y j roof. And which r is equal to rt, which is a function of time. And this is called the plane curve motion equation. And this motion equation has two components. It has x equals xt and y equals yt. That means this plane curve motion can be decomposed into two linear motion, which is the x direction and y direction, and they are perpendicular. From the previous equation, x equals xt and y equals yt, if we can eliminate the time parameter t, and thus we get the motion orbit, that is y equals yx, that's the orbit of this particle. So that like t in physics represent time, but in math it can be abstract to a certain parameter, whatever. We consider a case where there was a point P and it's moved towards a point Q. This is a curve. So at first, this is our position R, and then at point Q, this is our position RT plus delta t, which the objects move from point P to point Q in an interval of delta t. So we can see that this is delta y, it's changing delta y, and it's changing delta x. And this total change is delta r. So the displacement we can thus written from P to Q in time interval delta t as delta r equals rt plus delta t minus r at time t. And this delta r is a vector, and its two component delta x, I roof plus delta y, j roof, those are its two component. So it's not hard to imagine that if delta t goes smaller and smaller, the point Q goes gradually approaching point P, the origin point. Not origin, but the initial point, I mean. So that those delta R becoming most likely to becoming tangential to the curve at point P, which we call Pm. Suppose delta t is an infinitely small quantity dt, then Q is infinitely approach P. And those infinitely small displacement dr is parallel to Pm. So this has two components, dxi and dyj. And the particle at time t, the instant velocity is, we can just call the velocity, is defined as dr dt, which this v is tangential to this curve at point P, and exactly at time t. So v can be decomposed into vx I roof plus vy j roof. And vx as defined is dx dt and vy equals dy dt. So those can be either positive or negative, it doesn't matter. It only matters to the direction. So it's called like the decomposition of the speed v. So the absolute value of it, the speed, is equal to vx squared plus vy squared, which we can easily see like from the graph. From interval t to t plus dt, in this infinitely small time interval, the change in the particle velocity and its components are dv equals vt plus dt minus vt, and dv equals dvx I roof plus dvy j roof. Let's make it a little bit more clear. It's a dt. So that the particle at time t has an instant acceleration. We can just call it as acceleration, which is defined as a equals dv dt. And do the same way, it's equal to ax I roof plus ay j roof. And ax equals dvx dt equals d squared x dt squared. Ay equals dvy dt equals d squared y dt squared. That is exactly means a equals d squared or dt squared. So that from this point we can see that actually this plane curve movement r has a similarity towards our position x with linear movement. That's just this r has two components. It's almost the same. Then we consider the case where our object is ejected at an angle zeta apart from the positive direction of the x-axis with the initial velocity v0. So we can see it will be a parabola and it got the height h and goes a distance s. So there is a point P where our object is. So that we can define that when this object is ejected, then that's time t equals 0. You can define any time, but this is the most convenient way. So we have x0 equals 0, y0 equals 0. And we have vx0 equals v0 cosine zeta. Ax equals 0. Vy0 equals v0 sine zeta. Ay equals minus g, right? Because it's just acceleration downwards. And this v, the relationship come from the component. So before it's landing the y direction, it goes a constant acceleration linear movement. So that it was exactly like ejected from in initial velocity of vy0 upwards. So we used the conclusion before, vy equals vy0 plus ayt equals v0 sine zeta minus gt. So y equals y0 plus vy0t plus 1/2 ayt squared equals v0 sine zeta t minus 1/2 gt squared. And then we can get the x direction. Before landing, the x direction goes like a constant velocity linear movement, right? So we also have vx equals v0 cosine zeta, and x equals v0 cosine zeta t. Let this be 1 and 2 equations. Now we combine the equation 1 and the equation 2. We combined and we eliminate t, so that we got y equals minus g divided by 2v0 squared cosine squared zeta, x squared plus tangent zeta dot x. This is easy to do, that you can just substitute t equals x divided by v0 cosine zeta and substitute this t to equation 1. You will get exactly this answer. And from your geometry class, you may have learned that cosine squared zeta over 1 equals sec squared zeta equals tangent squared zeta plus 1. So this equation 3, this orbit, can also be written as letting tangent zeta equals u as y equals minus g over 2v0 squared x squared 1 plus u squared plus u dot x. This is like often also like frequently used, because when you want to get an outside cost of this curve, you make that a function of u, and this is a power of 2. The u function, we have a u squared u that is easier to discuss than just have cosine zeta or tangent zeta. Since it was a parabola, we want to know that when p reaches highest point, what is that height? So when it's reached the highest point, we can easily see that it's vy equals 0, right? It's began to decelerate and to the velocity is 0, and then accelerate again downwards. So that we substitute vy equals 0, we got that th represented at this point h, that is go through this th of time, is v0 sine zeta divided by g. From this point, we also want to know, like, what is the height? The height can be easily calculated. Just substitute this th back to the equation y equals v0 sine zeta t minus 1/2 gt squared. Right, just substitute this th back and our y is h. Make this a little bit clearer. And we get the h is v0 squared sine squared zeta divided by 2g. It's just substitute back, use simple trivial algebra. And then we want to know how far it can go. This s, this distance s. So that we refer to the previous equation that x equals v0 cosine zeta t. So what is this ts? Like from symmetry, we can easily see that the time goes up through h. The origin point O to h is exactly the same as h to the ground, which we can also see from the equations, right? So ts is simply 2th. So it is simply 2 v0 sine zeta divided by g. So we can just substitute back to this x, and we get s equals v0 squared sine 2 zeta divided by g. And this uses sine 2 zeta equals 2 sine zeta cosine zeta, which you all have learned in your geometry class and algebra.